All right. Oh, and I should also mute people. We've been through this before. Okay. All right. So before I get to the class time here, it's appropriate. I've got 10 minutes before the crypto class starts. This is not cryptography, but it is bloody awesome. I've been struggling with exploiting domain controllers and pivoting for 124 and for my students that are doing OSCP and for the students in the CPTC contest. Yeah.
You said USC?
US what?
UAC? I can't hear you, I'm sorry.
Oh, okay. I'm working on how to exploit domain controllers.
Okay.
There's a variety of my students for needing this for various reasons. And I found that I could, I set up a Windows Server 2008 domain controller and member server, and it was so buggy that I couldn't get anything done. See, the problem is we don't have access to client machines anymore because of the City College purchase process not moving. So we don't have Windows 7, Windows 8, or Windows 10 available for students to use right now. So I'm using servers as clients. Anyway, the point is I upgraded to Windows Server 2012, R2, and once I was able to exploit that and get a shell on it, I couldn't elevate the system privileges. I couldn't find any exploits that worked anymore. Yeah?
Because of UAC?
Even when I turned off UAC, I still couldn't find any that worked. Because it's fairly new and fairly well patched. But then I finally found one. It's not in Metasploit. I did Eternal Blue a couple weeks ago, which is one of the ones the Russians dumped in April. The Russians dumped official NSA attacks, and now I got Eternal Romance. Eternal Romance is unbelievable. Eternal Romance, I can't understand why it's not in the headlines. It is the new MSO867. It exploits every version of Windows with no user interaction and gives you system control. Every version, they say, and I got it working on Server 2012 R264, and the guy says it works on 2016 also, and on everything else. However, there is a condition, although it's not much of a condition. You have to have file or printer sharing turned on, and it has to have some account that can connect to the file or printer sharing service, which is not usually asking too much because many servers have that, and you take over some desktop by getting someone to click on a link, and then you have some access to it. But anyway, here's all it is. I'm going to have it as a project in 124 soon, but I got it working here. What happens is you download this thing, 42315 is the exploit, and that thing is kind of long. It's a long Python file. But here's what it works on. Every bloody version of Windows you could imagine, from 2008, 2003, 7, 8, 10, XP, 2003, everything. That's why, the NSA is not messing around. When they're taking you over, you're going down. So you need a username and password that can connect, and what I've done is just turn on unauthenticated file sharing so the guest account can get in. You could put in a name and password if you have even one name and password that can get on. And then you can just run this thing. All you do is run that script. You have to download this MySMB library, which is just a Python library to connect to an SMB share. So that's nothing surprising. And then you just run the exploit and IP address, and you have to have a named pipe that exists, and two named pipes that always exist are spool SS and browser. Those are Windows services that are listening to do printer spooling and to decide and to inform machines that a share is available. So when they go to like network neighborhood or whatever the latest version of it is, they can see it. So you run this thing, and what it does, this just to prove that you own the box, it creates a file cpwned on the box, and there it is. So this is my Windows 12 R2 server, and let's delete this thing and run it again, and there you see it creates that pwn file. So now I think Microsoft patched it. That was the point. That was why the WannaCry worm spread around the world, because people didn't patch their stuff. Microsoft somehow found out about this back in March, before the Russians dumped it. Somebody leaked it to Microsoft and they put out a patch. So it's only going to affect you if you haven't put on all your patches. So, but anyway, I'm thinking it probably did hit the news in the sense that the WannaCry worm hit the news. But anyway, it's pretty impressive. And pen testers have been using MSO867 for almost 10 years. But MSO867 quit working when we quit using Windows XP. And this, as far as I can see, is the next step up. This will work on anything that isn't updated, like that's more than 3 or 4 months out of date. And in practice, people could keep using MSO867 for almost 10 years because there's always some clown that didn't put on their patches. Anyway, so that's pretty awesome.
So limitations as far as where you can dump payload?
No, it doesn't dump payload. It executes a command line, any command line you want. You can, and that's what the rest of this, I'll have a project probably by tomorrow in 124. It executes any payload you want. So it's bloody awesome. Anyway, let me see if I got any scheduling notes to make or anything. Let's see, it's 6:07. Yeah, time does it put the schedule on the wall. This is 141. And today is September 25. All right. Today. Is, project 4 and 5 do. And next week is 10-2, project 6-2. And I guess quiz chapter 5, yeah. All right. Anyway, so let me just a couple of minutes, see if anything else is worth mentioning. I don't think anything, yeah. Yeah, there's stuff coming up, but not much of it is. There's CactusCon, several of us are going there, but people that haven't planned to travel might not want to travel to Phoenix. There's 2600 meeting, which is more of a social meeting. Silicon Valley Code Camp is coming up. It's on the same weekend as the Collegiate Pen Testing Championship. So I think we'll be going to those two things that weekend. Anyway, nothing too exciting. Here's the finals, but this is the regional, which is in town at Uber. So I'm going to have to figure out how to cope with the fact. I think they've approved my talk, but they haven't. And if they haven't told me when it is. Anyway, I may have a scheduling conflict there, but we'll see what happens. Anyway, today we're up to chapter 4, and this is 141. And there we go. All right. And supposedly you've got it all available here. Find the right semester. Somebody told me one time these things didn't work, so maybe I'll take a look. 4. Yeah. All right, good. So you should be able to get the slides. Fair enough.
Quick question.
Yeah.
This is online live right now, right?
Yes.
Is there a link for that?
Yes. Yes, right up here. Zoom. Right there. Good, sure. Good. All right. As you see, a lot of people are coming in online. All right. So let's break this to start. All right, so here we are. We're up to AES, probably the most important cryptography. The most important stuff to know is AES and RSA. Those are the main routines you use, and there are some things that support them, like PBKDF2, which lets you derive a key from a password, and is very closely related to the password hashing functions used in Linux. But the two main routines used for it, or Tom, for real cryptography are AES and RSA. So here's the game here. All right, so AES is the replacement of DES approved by the government. It is, as far as anybody knows, completely unbreakable in all its versions. The only thing that makes people at all nervous about it is quantum computers. And even quantum computers will not be able to break it if you choose the stronger versions with a 192 or 256-bit key. And there is no available quantum computer that anybody knows about that can really do anything yet. So currently, there is nothing anybody knows that will get in here without the key. However, you can make mistakes in how you implement it in hardware or software and leak out the key through side channels, and that happens a lot. But the mathematical system is, as far as anybody knows, unbreakable. So this came out in 1997. In the late 90s, various people, as we talked about last time, proved beyond a doubt that DES was shot and something better was needed. So the National Bureau of Standards, which later became NIST, well, it may have already been NIST at that time. Anyway, they They asked for algorithms, and they got 15 candidates and 5 finalists. And as I mentioned before, for all practical purposes, all the finalists are fine. They got to the final because there was nothing significant wrong with them. Then they just had to pick one to give the prize to. But it doesn't mean in any way that anybody found a way to hack the others. And so if you are selling a product to the government or dealing with other major businesses that deal with the government, then you use AES to be consistent with what they expect. If you are some kind of political rebel or suspicious type person, or you're building some privacy product that you want to protect from the government, you might prefer to use one of these others on the hypothesis that the government secretly backdoored AES. There is no evidence of that, but how would we ever know? Anyway, so RINJail was the algorithm chosen and approved as AES in 2001. And it's improved not only for business use, but also for military secrets, top secret for the longer lengths. So it's very, very trusted by the US government and by everybody else around the world. So here's how it works. Remember, all these things are combination ciphers that just have multiple rounds that do things. So there are, a key comes in, the plain text comes in the top, 128 bits, 128 bits of ciphertext, and Y comes out the bottom, and the key comes in the side, and that's the game. And then it's done with a bunch of rounds, and the key lengths determine the number of rounds, 10, 12, or 14. So it's an iterated cipher. Each round has layers, and unlike DES, 128 bits are encrypted in each round. Remember, DES had this crazy Feistel thing where only half the bits are encrypted and the other half are used to create the round key. So you have to keep swapping them. And if you have 16 rounds, each half only really gets encrypted 8 times. AES does not work that way. Every bit of it is encrypted every time. All right, so there's 3 kinds of layers. There's a key addition layer where you XOR this to the state table. Then there's a byte substitution layer, which is an S box to give you confusion. So the relationship between the key and the ciphertext varies. And then there's the diffusion layer to give you the other desirable property. Remember, we want confusion and diffusion, and that's shift rows and mixed columns. Confusion makes sure that changing one bit of the key changes bits all over the answer, and diffusion makes sure that changing one bit of the plain text changes bits all over the answer, so that even if you that there are no patterns in the answer that can be used backwards to deduce the key or the plain text.
So what is that? The confusion zone?
Confusion means that the key is not related to the answer in any clear way. Changing one bit in the key changes all the bits in the answer. Really, half the bits all over it.
Do that with a sort? Or
You do that with what?
with a sort function or XOR function?
Yes, you do it with a substitution. That's typically, substitution is what you do. For example, the simple substitution cipher, the Caesar cipher, has confusion. You move every letter forward in the alphabet. Now, if you change the key by even one number, all the bytes, all the letters change. So there's not any part of the ciphertext you can use to deduce what part of the key changed. So substitution is typically the operation that gives you confusion. Okay? And diffusion is the operation that means changing a bit of plain text will only change one bit of the ciphertext. The Caesar cipher is a confusion cipher, but it lacks diffusion. If you change the key, every character in the output changes. But if you change one character of the input, only one character of the output changes. So it doesn't have diffusion, but it does have confusion. Okay? All right, anyway, so that's, and you need both of these things. And as we said, the right way to do it is to have several rounds where you confuse and diffuse, and then confuse and diffuse again, and confuse and diffuse. And that's how you make something that is really, really hard to reverse without the key. So I got a video playing this animation here, which is good at link 4A. This had a fun Flash animation, but Flash is over, man. So there we are. So YouTube video is probably the best way to do it. All right, so here is RINJail. So in comes plain text at the top, ciphertext out the bottom, and the keys come in the side. So your key is 128 bits, which looks like that, 4 by 4 bytes. Let me stop it and go back a bit. All right, So your key is 4 bytes by 4 bytes. That's the 128. And you're going to have this state function created that moves forward as you move through the encryption process. All right. So here's the overview of the general encryption process. You add a round key, which is actually XORed in. Then you have substitute bytes, shift rows, mix columns, and add another round key. You do this 9 times, and the last time you skip 1 step. That's all. So it's obviously doing the same kind of manipulations we've seen in DES and other ciphers. This is the combination that's considered most secure these days. So there you go. 9 rounds of this. And then the last round is a little different, and then you're done. So there's 4 transformations. You substitute bytes by using this S box, which we also saw one like this in DES. So you have an S box, which I think is always the same, and it is chosen just to scramble the bits. And then you shift rows, like this, to break up vertical stripes, to smear them out. And then you mix columns this way, with matrix multiplication, to break horizontal stripes. So what you can see, this is just the same way you make hash. You cut it up this way, you turn it, you cut it up that way, you scramble it, you cut it up again. You're just mixing the bits this way, mix them that way. You're trying to make sure that all the bits are scrambled so that there's no pattern in the output that gives the attacker any clue about what the key was or what the plain text was. That's all you're doing. But there's nothing random at any step. It's all completely determined by the key because you have to be able to reverse it with the key. So then you add a round key to it. All right. And that's it. See if there's anything else important coming by here. Oh, they're going to say something about the key schedule, I think. Remember, the key schedule just involved rotating bits around for DES, the 16 bits. And let's see what the key schedule looks like here. Okay. That's what I thought. You do the same kind of thing you did for DES. You rotate the bits around, run it through an S box substitution. You're using the 128-bit input key to just create a whole bunch of other keys, a different one for each round, but all created in a deterministic way from the first key. And again, all they do is scramble everything. So one bit of the key moves around to this round it's here, next round it's here, this round it's here. So that bit touches every part of the encryption and gets smeared out through the whole thing. All right, so that's the game. That's the general outline of AES. All right, and I've got a few Kahoots about that. So let me open my Kahoot. All right, and sign in. My Kahoots are here. Okay, 141 AES. All right. This looks good. Okay. Wow, a lot of people online. Well, that's fine. All right. So there you are, 203, 141. I better get a piece of paper to write the winners now. All right, got 23. All right, they're still coming. I'll wait a few more seconds. Gotta write this attendance sheet anyway. I'll put mark on here.
Does this cost money?
No, it's free.
Your cell phone.
I don't know. So what's that? I don't know. From somewhere in Italy. That's a good question. I don't know how they're paying for it. It may go away someday. So I saved my questions. I could go back to the iClickers if I had to. All right, how many bytes does AES encrypt at a time? All right, 16 bytes, 128 bits. All right. How many key sizes does it have? All right, 3, of course. Okay. So what system is approved for secret but not top secret? That's AES 128. And all right, and I don't think they knew this when they had defined that, but a good way to remember it is because this one is not going to survive the coming of quantum computers. They'll have to quit using it. Because quantum computers can guess 2 to the 128 keys by only doing 2 to the 64 operations. And 2 to the 64 operations is achievable. So anyway, all right. What process makes the ciphertext look unrelated to the key? All right, that is confusion. All right, how many rounds in AES? That's it. There are 3 kinds, and they are different. All right, good. I got 3 winners. Cam, I know who that is. And Hurt. And Yo, who I'll have to identify later. All right, so we got time to carry on a bit more here. All right, so the internal structure works on bytes. You've got a 4x4 matrix of bytes, 16 bytes coming in, also 16 bytes for the key. And this is the input. This is a block of data coming in. So here's your round functions. You run it through an S box for substitution to create confusion. Then you have the diffusion layer that shifts rows and mixed columns. And then you add the key in with XOR. And let me see if I can get this thing out of the way. I don't know if there's any place that really gets it much out of the way. All right. Yeah, it's better. All right. And that's the game there. And in the last round, you skip 1 step. All right. So these are S boxes. They're identical. These are called a nonlinear element. They just move the bits sort of randomly back and forth. And of course, one issue is where they got the S boxes. There's the S box. It just looks random to me, but it is carefully chosen. And I'm not sure it's well known how they chose them. So the diffusion layer gives you diffusion. So every bit of the plain text is smeared all over the ciphertext. So you do it by shifting rows and then mixing columns. So you scramble it one way and you scramble it the other way to make sure that the bits have an effect randomly all over the whole ciphertext. So the rows are shifted cyclically. The first row is left alone. The next row rotates 1 to the left, and rotate 2 to the left, and rotate 3 to the left. So if there were vertical patterns, they get smeared out. And this does the other thing for horizontal patterns, combines them. All right. Then you have key addition. So you have a subkey, which is then XOR'd in. And the subkeys, they come from the key schedule. And the key schedule is just a way of flipping the bits around to make the required number of subkeys from the original 128-bit key. And as you see, you need the number of rounds plus 1 worth of subkeys, because you have 1 at the start and 1 at the end. Now, this is called key whitening. We've talked about this before. To make DES stronger, one thing you could do is add a 64-bit key and XOR it in before you do the 56-bit encryption and have another one at the end. And that would just mean you have more bits to guess. It'll help make up for the short key in DES. Here it's integrated. Built into AES is this XORing with something before and after, which amounts to key whitening. All right, so here's the key schedule. It works on 32 bits at a time. It stores subkeys all over the place. The first subkey is just the original AES key, and the next one scrambles it around. So you have a function that rotates its 4 input boxes, and you have a way of scrambling these keys around. We saw in the video, just rather like DES, breaks it into chunks and then rotates the chunks around, just to scramble the bits. All right, so now you got to implement it somehow. And this was designed carefully to use mathematical operations that processors can do efficiently. So the original plan was for 8-bit processors, but of course that's obsolete now. And if you want to do it efficiently on longer processors, it turns out to be much better to just merge all the operations into one big table lookup, rather than try to do them, because you're moving bits one by one, moving bytes one by one, and it kind of wastes the value of 32 and 64-bit processors to do it that way. So it can be very fast if implemented correctly with a lookup table on a modern processor. What's that?
Question. Can you
Yeah.
explain the 16 table lookup thing?
What's that?
Can you explain the 16 table lookups?
Yeah, you have to make a lookup, but it's not that big. 256 entries with 32 bits wide, so it's not a very large table you need.
No, can you explain the 16 number?
Oh, no, I can't. I don't know where the 16 comes from. It's a good question, and I don't know the answer. I imagine it means you're doing 4 bits at a time, but I'm guessing. All right. So here's the security. You can't do a brute force attack because even 2 to the 128 is completely out of range. Remember, 2 to the 56 was barely possible in 97. 2 to the 64 fell a few years later. 2 to the 72 has never been cracked by brute force, and people expect it to take the next 1,000 years to be cracked. So anything much longer than 72 is just impossible now or any reasonable time in the future, unless we get quantum computers, which will, of course, make things different. Now, I just saw something happen up here. Let me see if I can deduce something. I think I saw something happen here. Chat, aha. Can the person on the phone take his call somewhere else? I thought I had muted everybody. Let me try it again. Theoretically, I muted people. Mute. There. All right. Theoretically, you're all muted. Let me know if they still can't hear anything. I appreciate it, because I have no way to know what you're hearing at the other end of this. And if it's no good, let me know. All right, anyway, there's no analytical attacks, which is nice. There is no mathematical trick that lets you break it without trying all the keys, like there was with WEP. And so those are good. As far as the mathematics is concerned, AES is, as far as anybody knows, perfect. The only thing you can do is brute force attack, and the key is long enough that a brute force attack appears to be impossible. So the only thing that can go wrong with it is side channel attacks. If you do something stupid in the implementation, like store the key someplace it can be stolen, then of course it can be cracked that way. Yeah.
So why do they not allow the larger block sizes like 192 or 256 at the mentioned algorithm? When they chose AES, why did they limit it to what? Is it an efficiency issue? Or?
I don't know. It's a very good question, and I'm not even sure that information is public. The question is, why didn't they increase the block size along with the key size?
Because the algorithm allows it.
I think the algorithm could have tried, but I mean, I don't think there's any reason to have a larger block size. That was their idea. And theoretically, AES 256 will even survive quantum encryption. So I think as far as anybody knows, they didn't cheat us this time. They totally cheated us with DES and with elliptical curve cryptography. Both of those, one version of those were poisoned. They were poisoned by the NSA that totally ordered NIST to lie about them. And no one's ever found any evidence that they did that with AES. So if they lied about AES, they were much more successful at getting away with it. Anyway, that's a very good point. So a side channel attack looks for some error you've made that is not a mathematical error, but some handling issue. For example, you can watch the power consumption. Let's see what's happening here. There's more information. Can you repeat? Yeah, I did that. All right, good. Okay, good. Anyway, so here's how you do it in Python. Remember, this is my plan here. We should play with it and see how it looks. So let's do here and make this fit on the screen and shove this to the side. All right, so 10 minutes, that's good enough to go along here. Okay, so let's do Python. You can just do it in immediate mode for simple calculations. And from crypto.cipher, import AES. All right, now you make a key. It has to be exactly 16 bytes long. So I chose this, that's 16 bytes. And by the way, you can check that with length. All right, it's 16 bytes. All right, so now you put in your plain text, which also has to be 16 bytes. And let's check that. All right, now you create a new AES object. And the only thing you need in the default mode is the key. There is no IV in the default mode, which is ECB. More about that next time. This is not the wisest choice, but it's the easiest to get started. And now you can just do ciphertext encode. I'm going to put it in a variable so we can refer to it. Cipher encrypt encode, pardon me. Cipher encrypt plain, pardon me, okay. All right, that's going to do the encryption, and I can print it. Ciphertext, I'm used to tab completion. All right, and remember from before, ciphertext is now a 16-byte string, but it's binary. It's probably not going to be printable, so it's going to look like dirt. So the way to make it look good is to encode it as hex. So it does not attempt to print it as ASCII, and now you get a long hexadecimal string. That is the encrypted. The plain text is secret, 16 bytes. It's now encrypted like that. And remember, we've done this before. If you were to change the key by a small amount. So the key was 16-byte key. All right, so if I make that a Z, that's only going to change 1 or 2 bits of the key right at the end. So save that. Now I make a new AES object, and I calculate the ciphertext of that and print it. There we are. And you can see this is confusion. If I change the key by 1 bit, I change everything. 87B, 95, the middle, middle and end, every part of it changes. That's what you want. You want the key, changing 1 bit in the key to have no pattern. Change half the bits randomly all over the answer.
That's different, right?
What's that?
That's different.
That's confusion. Diffusion means that 1 bit of plain text changes it. So let's try that too. Let's go look at our plain text, which is here. Okay, and change that to a T. That will change 1 bit of plain text. This is diffusion. And save that. And now I got to make a new object. Probably could have used the same object since the key didn't change, but anyway. And this is the answer. All right. So now I've changed 1 bit of the plain text, and again, everything's changed. 38 to CC, 53 to D7. That's what you want. This cipher has good confusion and good diffusion. And that's what you want. And of course, you can decrypt it by just cipher.decrypt. There. And I don't need to store it in a variable. I just need to decrypt, and I need to put in ciphertext here. And then it will take me back to my plain text, which now ends in a T. So those are the simple things you can do here. And in the next chapter, we're going to go more into the different modes of encryption. The default mode here has no initialization vector, which is a problem. And in fact, I can show you something fun about that right away. Let's take this and put in the same stuff again. 16 byte. There. Suppose I have 2 of them. Okay. And now I encrypt it. Yeah, well, I have to encrypt them. In fact, it's kind of obvious. I'd have to encrypt them, one group of 16 and the next group of 16. And since there is no randomness, I'm going to get the same answer both times. So if you have patterns in the input, you're going to see patterns in the output with this mode, and we're going to deal with that next time. Anyway, all right, and I think that's it. I'm down to the Cahoots. I'm going to stop and restart the share so the remote viewers have a chance to see it. And then I'll show you a, let me stop this. I'll start it.